Good morning, everyone. My name is Thanaphon Grace, and I am here together with my colleagues, Nutt Tananimit from the DeepMath AI Research Group. Today, we are presenting our work titled Fixed Time Gradient Neural Network for Absolute Value Equations at CMMSE 2026. I will now hand over to Nat to give a brief overview of what we will cover today.
Okay, thank you, Grace. The absolute value equation, or AVE, has a wide range of applications in optimization and complementarity problems. Despite its simple form, AVE is an NP-hard problem. Solving the AVE efficiently and reliably, especially under noisy conditions, remains a challenging problem. In this talk, we propose a new continuous time neural network called the Fixed Time Gradient Neural Network, or FGNN, designed specifically to solve the AVE with provable fixed time convergence guarantees. I will let Grace walk you through the outline of our presentation.
Let me begin by giving you a roadmap of the talk. We start with preliminaries, covering the key background on fixed time stability and the absolute value equation, or AVE, that our method is designed to solve. Next, FGNN dynamics. We will introduce the network architecture itself, a polynomial gain design with a three-term structure and hyperbolic smoothing. The heart of the talk is section 3, main results. We establish fixed time stability of the unperturbed network, and then prove 4 robustness theorems covering both vanishing and non-vanishing noise scenarios, addressing both convergence and boundedness in each case. We then step back in section 4 to survey the broader AVE solver landscape, comparing 9 continuous time models to put our contribution in context. Section 5 presents numerical experiments where FGNN is tested against 8 baselines across 4 different noise regimes. In section 6, we discuss the shortcomings of exponential gain designs and explain why polynomial gains are the more practical choice. And finally, we close with summary and future work. Let's get started.
Okay, let's begin with the preliminaries. The key concept is fixed time stability. Due to Polyakov in 2012, the origin of a dynamical system y dot equals f of y is globally fixed time stable if it is globally finite time stable, and there exists a uniform upper bound T max such that every trajectory converges to the origin within T max, regardless of initial condition y naught. Now, to certify fixed time stability in practice, we use the lemma fixed time if we can find a Lyapunov function v that is positive, radially unbounded, and whose time derivative satisfies v dot is at most negative zeta 1 v to the power of k1 minus zeta 2 v to the power k2 with zeta 1 and zeta 2 positive, and k1 is strictly between 0 and 1 and k2 positive, k2 greater than 1, then the origin is globally fixed time stable with the time bound as shown. This is the key lemma we will invoke later in our stability proof. Now finally, we also need the fixed time attractive set lemma here under the same Lyapunov condition, but for V exceeding some threshold R, then the sublevel set here where V is at most R become globally fixed time attractive with the same time bound. This will be essential when we analyze robustness under insufficient gain. Now let me introduce the problem we are solving. The absolute value equation, or AVE, takes the form of A minus the absolute value of x equals b, where A is an n by n real matrix and b is a vector of length n. A unique solution x star is guaranteed whenever the norm of A inverse is strictly less than 1, which implies that the norm of A itself is greater than 1. This is the condition we assume throughout our work. Now, to solve the AVE using gradient neural network, we need to handle the non-differentiability at 0. We utilize hyperbolic smoothing S tau with parameter tau greater than 0. The Jacobian of this smooth system is J of x equals A minus D, where D of x is the diagonal matrix as shown here. So, why do we use hyperbolic smoothing? The first reason is that each entry of the diagonal matrix D is bounded by 1. So the norm of D is at most 1. This is crucial for lemma J sigma that we will see later. The second is that the Taylor expansion of the hyperbolic term has second order accuracy. So it is negligible for small tau. With the problem formulated, let me now present the neural network we propose. The fixed time gradient neural network, or FGNN, evolves according to a piecewise ODE. When S tau of x is non-zero, the state x evolves as shown here. And when S tau of x equals 0, that is, when we have reached the solution, x dot is set to 0. The parameters x, c1, c2, and c3 are all positive, with k1 strictly between 0 and 1, and k2 is greater than 1. The design follows three-term gain structure. Each term plays a distinct role. The C1 term dominates near equilibrium. It provides the fine scale pool that drives the residual to 0 in finite time. The C2 term dominates far from equilibrium. It ensures rapid initial descent Together with C1 term, they enable fixed time convergence. And the C3 term is the robustness key. It counteracts non-vanishing noise and keeps the trajectory bounded up under persistent perturbations. This is a crucial auxiliary lemma, which we call lemma J sigma. There exists a constant sigma greater than 0 such that the norm of J of x times S tau of x is at least sigma times the norm of S tau of x for all x in Rn. Let's take a look at the proof sketch. We can factor the Jacobian J equals A times I minus A inverse D. And since the norm of A inverse is less than 1 by our assumption, and the norm of D is not exceeding 1 due to our choice of the smoothing function, J must be invertible. We bound the norm of J inverse using Newman series. This gives the norm of J inverse is bounded by this term, and in turn it is bounded by this term. Now take the smallest singular value of J, which we call sigma. It equals the reciprocal of the norm of J inverse and is therefore strictly greater than 0. For any vector v, we have the norm of J times v is at least sigma times the norm of v. Taking v to be S tau of x, it gives us out the lemma. So why does this matter? Every step of our Lyapunov analysis produces bounds in terms of norm of J of x times S tau of x. Lemma J sigma converts them to the norm of S tau square, which is exactly our Lyapunov function. Moreover, sigma depends only on the norm of A inverse. It is a problem constant, not state dependent, nor initial condition dependent. Now we have arrived at the main result of this work. The theorem states that the equilibrium point x star of the FGNN is globally fixed time stable. Let me walk you through the proof sketch. We choose the Lyapunov candidate V equal to the squared norm of S tau of x. Next, we obtain the bound V dot as shown here. Note that we drop the C3 term since it is non-negative. Now, we invoke lemma J sigma. It gives us that the norm of J of x times x tau of x is at least sigma V to the 1/2 here. So substituting this into our V dot bound yields step 4. This is precisely the structure required by Polyakov's fixed time Lyapunov condition from type 1. Therefore, x star is fixed time stable with the time bound as shown. This bound is finite and uniform. It does not depend on the initial condition, which is the essence of fixed time stability. Now, we consider what happens when the network is perturbed by noise. The first robustness theorem handles vanishing noise. noise that is bounded proportionally to the residual. This means the noise vanishes as the system approaches equilibrium. The key condition is that M, the minimum gain of the network overall Rn, defined here, must exceed K. When this holds, X star remains fixed time stable even under this noise. Here is the proof sketch. Same Lyapunov candidate, V as before. After substituting the perturbed dynamics and applying the noise bound, V dot satisfies the inequality shown here with the noise contribution absorbed by the gain terms. We define epsilon as m minus k over m, which is positive by assumption. This lets us factor the bound into the cleaner form shown here. Applying lemma j sigma as before gives us the standard fixed time form in V as shown here. Therefore, X star is fixed time stable with the setting time bound T as shown here. Now it is scaled by epsilon to reflect the noise level. The key insight is that as long as the network gain dominates the noise, vanishing noise does not destroy fixed time stability. Now we tackle the non-vanishing noise. Here is the noise bound simply in the form of n of x is as mod k. It is a constant regardless of how close the system to the solution. The noise does not disappear at equilibrium, making it a much more demanding scenario. The condition for robustness is now the C-free term. If C3 is greater than or equal K, then X star remains fixed time stable. The proof is actually cleaner than the previous case. We take the same Lyapunov V as before. After expanding V dot with the perturbed dynamics, we get the bound as shown here. Now, let us observe these two terms. The term involving C3 and the noise bound K. Since C3 is at least K, the entire term is non-negative and we can simply drop it. What remains is exactly the same V dot bound as in the unperturbed case as shown here. Therefore, we can recover the same fixed time bound as the unperturbed network. This is the role of the C3 term in our three-term design. It was introduced precisely to absorb non-vanishing noise. By choosing C3 large enough to dominate the noise level K, the network behaves as if there were no noise at all. So, what happens when the gain conditions are not met? That is, when M is less than or equal to K in the vanishing noise case, or C3 is less than K in the non-vanishing noise? The answer is we can no longer guarantee convergence to X star exactly, but we can still guarantee fixed time boundedness to a small region around it. Both cases follow the same proof pattern, so let me describe them together. In both settings, we identify a ball B delta, defined as all x where the norm of S tau of x is at most z bar plus delta over sigma, and we show that this set is fixed time attractive. For vanishing noise, z bar is the largest root of the function h of z here. The attraction time t delta is given as shown here, with gamma depending on h evaluated at z bar plus delta. For non-vanishing noise, z bar is unique positive root of g of z here. The attraction time takes the same form, with gamma now defined as the infimum of g over the relevant region. The proof pattern is the same in both cases. Outside B delta, we show that V dot is bounded by -2 gamma times the standard fixed time expression as shown here. Applying lemma J sigma then gives us the fixed time Lyapunov form here, and the fixed time attractive set lemma from our preliminaries completes the argument. So even when the gain is insufficient, the FGNN still delivers a fixed time guarantee, just to a bounded region, and does not degenerate by diverging to infinity due to noise. Okay, let me now place our work in the context of existing methods. First, it helps to understand the convergence implication hierarchy. Predefined time implies fixed time, which implies finite time, which implies exponential, and which implies asymptotic. So fixed time, what FGNN achieves, sits near the strong end of this hierarchy. Looking at the comparison table of 9 continuous models, a few things stand out. First, our FGNN achieves fixed time convergence, handles both vanishing and non-vanishing noise, and is inverse free. That means it does not require computing a matrix inverse at each step. PRGNN by Yu et al., on the other hand, achieves predefined time convergence, which is even stronger, and also handles both noise types and is inverse free. FIX and JLHH by Zhu et al. Achieve fixed time convergence, but handle only vanishing noise here, and JLHH is not inverse free. FIN achieves finite time convergence with vanishing noise robustness. The remaining order models CYYH, MEAR, MAEE, and GNN achieve only exponential or asymptotic convergence with no noise robustness. The key observation is this: while PRGNN appears superior on paper, there is a critical practical limitation that we will revisit later, which is precisely the motivation of our polynomial gain design.
I will take it over from here. Now let's see how FGNN performs in practice. We test against 8 bit lines across four noise regimes, plotting relative error over time, starting with plot A. Bounded vanishing noise. FGNN converges rapidly to near matching precision and stay there, oscillating stably at the bottom. Most baselines are either divert or plateau at much higher error levels. In plot B, bounded non-vanishing noise. FGNN again converges to the matching precision and holds it. The majority of baselines either fails to convert and settle at significantly higher error. Move to plot C, large vanishing noise, a more demanding setting. FGNN still converges cleanly and remains stable at low error. Most baselines struggle considerably here. They either plateau to much higher noise levels or divert to infinity rapidly. Finally, plot D, large non-vanishing noise. The hardest regimes, FGNN converges to a bounded residual consistent with our theoretical prediction. Most baselines divert or plateau far above FGNN's level. Across all four regimes, FGNN consistently achieves the lowest error. This slide explains exactly why PRGNN underperformed in the experiment. PRGNN gain is proportional to the exponential of the square residual norm. So when the initial condition is far from equilibrium and the residual is large, the gain becomes astronomically large. This causes numerical overflow, producing non-value and effectively crashing the integrator. Okay, let's see from this picture. You can see this clearly here as the initial residual norm grows beyond the threshold around 10 square. PRGNN CPU time suddenly drops to near zero, not because it became faster, but because it fell immediately with overflow. The same pattern appears in the integration step count. PRGNN collapses at the same threshold, while FGNN line scales smoothly across the entire length. FGNN polynomial gain terms simply cannot overflow in the same way, making it practically robust to large or unpredictable initial conditions. The deployability implication is clear. In real systems, you cannot always control where the initial conditions start. An exponential gain design like PRGNN is too aggressive when started far from equilibrium. A polynomial gain design like FGNN is the safer and more practical choice. To conclude, let me summarize the four key contributions of this work. First, we propose FGNN, a polynomial gain gradient neural network that achieves fixed time convergence to the solution of the absolute value equation with an explicit settling time bound as shown here. Second, we establish complete robustness for theorems covering both vanishing and non-vanishing noise, addressing both convergence and boundedness in each case. Third, FGNN is inverse-free. No metric inversion is required at any step, making it computationally efficient and scalable. Fourth, FGNN is deployable. The polynomial gain design avoids the exponential overflow that plagues methods like PRGNN under large or unpredictable initial conditions. Before we close, let me briefly outline directions for future work. First, we plan to explore hardware implementation and circuit realization, bringing the FGNN dynamics into physical analog computing system. Second, we aim to extend the framework to time varying AT, where the system metric changes over time, which is common in real engineering applications. Third, we would like to validate the method against real-world noise benchmarks, moving beyond synthetic noise models used in our current experiment. Fourth, we are interested in developing adaptive gain mechanisms, allowing Psi 1, Psi 2, and Psi 3 to adjust automatically based on the current state, rather than being fixed in advance. And finally, we see potential in extending FGNN to broader problem classes, such as variational inequality and non-convex optimization. Thank you for your attention. We welcome any questions.